Hello students. In the last session, we had seen the phenomenon of refraction at plane interface of two transparent mediums. Today I will explain refraction at a spherical surface, that is a spherical interface of two transparent mediums. The laws of refraction are valid for spherical surfaces also, since very small part of such surface can be regarded as plane surface, and therefore same treatment could be done here also. First we will see how image is formed after refraction of light ray at spherical interface of two transparent mediums. Refer the diagram where we could see the positions of object O and image I on the principal axis of the spherical surface, having center of curvature C and radius of curvature R equal to PC. As the aperture, that is lateral size of the surface, is small, so the angles considered are also very small, and hence angle approximation can be made here. Also, the foot of normal is M, which is very close to the pole P of the surface. Therefore, we can measure the distances from M instead of P. In the diagram, we see that tan alpha is equal to Mn by Mo, tan beta is equal to Mn by Mi, and tan gamma is equal to Mn by Mc, which simply could be taken as alpha is equal to Mn by Mo, beta is equal to Mn by Mi, and gamma is equal to Mn by Mc. We also see that in triangle ONC, I is equal to gamma plus alpha, and in triangle INC, R is equal to gamma minus beta. Substituting the values of alpha, beta and gamma here, we get I is equal to Mn by Mc plus Mn by Mo, and R is equal to Mn by Mc minus Mn by Mi. According to Snell's law, mu1 sin I is equal to mu2 sin R, or simply mu1 I is equal to mu2 R, as angles are small. Substituting values of I and R here, the relation becomes mu1 times Mn by Mc plus Mn by Mo is equal to mu2 times Mn by Mc minus Mn by Mi. Mn being common is eliminated, and rearranging the terms, the relation becomes mu1 by Mo plus mu2 by Mi is equal to mu2 minus mu1 times 1 by Mc. Using Cartesian sign convention, we see that the object distance Mo is equal to minus u, image distance Mi is equal to v, and radius of curvature Mc is equal to r. Finally, we get mu1 by minus u plus mu2 by v is equal to mu2 minus mu1 times 1 by r. This relation we obtain when refraction takes place at spherical interface, when light ray moves from rarer to denser medium and mu2 is greater than mu1, for example from air to glass. Similar relation is obtained in same manner when light moves from denser to rarer medium, and that relation is mu2 by minus u plus mu1 by v is equal to mu1 minus mu2 times 1 by r. These two relations, which are true for both real and virtual images, are used to formulate the lens maker's formula, which is helpful in designing the lenses of desired focal lengths. Before deriving that formula, let us first know about the lens. Lens is a transparent optical medium bound by two surfaces, one of which is at least spherical. We normally make use of thin lenses. Depending on the shape of the surfaces, we name the lenses like double convex, concavo-convex, plano-convex, etc. In a lens, there are two foci, f and f dash, of double convex or double concave lens. The focus on the same side of the source of light is called first focus, and the other is called second focus or focal point. To find the image of an object formed by a lens, we can consider any two rays emanating from a point object, tracing their paths using laws of refraction, and finding the point where the refracted ray actually meet or appear to meet. We can choose any two of the rays. Number 1, a ray parallel to the principal axis of the lens, which after refraction passes through the second focus f dash in a convex lens, or appear to diverge from the first focus f in a concave lens. Number 2, a ray of light passing through the optical center of the lens, which goes undeviated after refraction. And number 3, a ray passing through the first focus of a convex lens or appearing to meet at that of a concave lens emerges parallel to the principal axis after refraction. Now to derive the lens maker's formula, we can consider the image formation by a double convex lens in two steps. As shown in the diagram, first image I1 is formed by the first refracting surface, and for that the object distance P1O is equal to U, image distance P1I1 is equal to V1, and radius of curvature P1C1 is equal to R1. Sign convention is already appeared in the formula. I1 is real image of object due to refraction at first surface. Therefore, mu1 by minus u plus mu2 by v1 is equal to mu2 minus mu1 times 1 by r1. For second surface, image distance p2i is equal to v and radius of curvature p2c2 is equal to r2. I1 serves as object for refraction at second surface. Therefore, mu2 by minus v1 plus mu1 by v is equal to mu1 minus mu2 times 1 by r2. Adding these two equations, we get mu1 by minus u plus mu1 by v is equal to mu2 minus mu1 times 1 by r1 minus 1 by r2. Taking mu1 common and shifting towards the other side, the relation becomes 1 by v minus 1 by u is equal to mu2 by mu1 minus 1 times 1 by r1 minus 1 by r2, or 1 by v minus 1 by u is equal to mu minus 1 times 1 by r1 minus 1 by r2, where mu is equal to mu2 by mu1. If the object is at infinity, the image is formed at the focus of the lens. That is when u is equal to infinity, v is equal to f. The relation then becomes 1 by f minus 1 by infinity is equal to mu minus 1 times 1 by r1 minus 1 by r2. And finally, it is 1 by f is equal to mu minus 1 times 1 by r1 minus 1 by r2. This relation is the well-known lens maker's formula. Well, the other details about thin lenses will be discussed in the next lesson.